Good day, students. The main concept of Unit 3 deals with magnetic field intensity due to the finite and infinite current element. In Unit 1, you have learned the same concept in terms of electric field intensity. So, the first two units, again, I'm repeating, it is electric field analysis. Unit 3 and 4 speaks about the magnetic field analysis. Unit 1 and 2 speaks about Coulomb's law and the analysis of your Gauss law. Here it is Biot-Savart's law and the Ampere-Circuital law. So let me speak about the magnetic field intensity due to finite and infinite current element. Now you are considering a line element which is carrying a current I along the z-axis. This is z-axis. So you can mark even here, it is z representation. Okay. Now dl is defined by dz of az vector. Whereas it is carrying current I, so I dl becomes equal to I dz of az vector. Now the lower end of this conductor makes an angle of alpha 1 and the upper end of the conductor makes an angle of alpha 2 with respect to the point P. How are we defining this point P? You are drawing a perpendicular bisector with respect to the line element from the z-axis. From point P, with respect to point P, we are drawing the perpendicular bisector such that it makes angle of alpha 1, alpha 2. This is the analysis. So alpha is lying between alpha 1 and alpha 2, which is with respect to the line element. As you know clearly, it is defined in the analysis of cylindrical ordinate system. The point is located at rho, phi, z. It is x, o, y plane. So it is a definition of x, o, y plane. So when I say x, o, y plane, no z component. So rho, phi. So most of the books uses this denotation of r, phi. So r, phi, 0. But the line element is located along the z-axis as 0, phi, z. As we have seen in the circular sheet, this is also similar. So let me first find out the r vector, which is equal to r minus 0. So r of ar vector plus 0 a phi vector minus z of az vector. So this is r vector value. From this I can find out the magnitude r equal to root of r square plus z square. So I can write ar vector is equal to r vector divided by r, which is equal to this value. Now according to Biot-Savart's law, we know this definition. What is the definition speaking about? dH is equal to ideal cross ar vector divided by 4 pi r square. This is known definition by Biot-Savart's law. Now we will go into the analysis, for which case let me write I dz az vector, because I will write from this equation I dl cross ar vector. Okay, I dl is nothing but equal to I dz of az vector cross ar vector. Already we have calculated 4 pi r square. We know r value is root of r square plus z square, so it becomes root of r square plus z square the whole square. Now let me define I dz of, I am expanding this terms, r of az cross ar vector minus I dz of, again this term is inside the bracket, it is understood. I can expand the terms just like multiplication. So but it is a cross product. I dz of z value is as such, it is az cross az. You know, in your mathematical analysis of cross product, ar cross a phi is equal to az. Likewise, az cross ar is equal to a phi, etc. But az cross az is becoming equal to 0. So I have to find out az cross ar, which is nothing but equal to a phi vector. This is understood from this. Now I rewrite the equation. Az cross az is equal to 0. This becomes equal to 0. We are left out with I dz r of az cross ar vector by 4 pi of r square plus z square power 3 by 2. Now dH is equal to, rewrite the equation, I dz of r, a phi vector, 4 pi of r square plus z square power 3 by 2. I need h, so integrate both sides. Integral of I dz of r of a phi vector by 4 pi r square plus z square power 3 by 2. This is pure integration in mathematics. So we'll go back to the diagram, find out what is dz value, what is r square plus z square, and we'll find the analysis. By definition of this diagrammatic analysis, I have z to be defined in terms of alpha, sine of by cos of. So I can write z equal to r of tan alpha from the diagram. Therefore, dz is equal to r secant square alpha. Differentiate this on both sides. dz becomes equal to r is constant, tan alpha is secant square alpha d alpha. Find out r square plus z square power 3 by 2. So it is r square as such In the place of z square, r square, z tan square alpha I have substituted. R square take out common, 1 plus tan square alpha, which is nothing but equal to secant square alpha. So r cube secant cube alpha is the analysis. For finite, the limit is known, lower limit to upper limit, which is alpha 1 to alpha 2. Whereas for infinite condition, I have to identify the angle. How to identify the angle for the infinite condition? So it is substitute z equal to infinity in this equation. We have chosen z equal to r tan alpha. So alpha becomes equal to tan inverse of z by r. So if z is equal to infinity, tan inverse of infinity pi by 2. Likewise, z equal to minus infinity produces minus pi by 2. So I have two set of conditions now to be discussed. From the same equation, go back to the equation h equal to I by 4 pi. Rewrite the equation. Integral for finite element alpha 1 to alpha 2 r into r secant square alpha. I have just substituted the conditions. Here it is I dz value is r secant square alpha d alpha. So I have just substituted dz value as r secant square alpha d alpha of a phi vector divided by r cube secant cube alpha. So cancel out, take out the common terms, cancel it out. You know 1 by secant alpha is nothing but equal to cos alpha. Upon integration, it is sign representation, upper limit minus lower limit. So the final answer takes up the form of h equal to I by 4 pi r sin alpha 2 minus sin alpha 1 a phi vector. But for an infinite line element, what happens to h? As I told you, the limit is from minus pi by 2 to plus pi by 2 if it becomes infinity, as we have seen in the previous analysis. So h is equal to I by 4 pi r of minus pi by 2 to plus pi by 2 cos alpha of d alpha a phi vector. Now substitute values of upper limit and lower limit. It gets reduces to this form. So cancel out the like terms. You are finally left out with the equation of h vector due to the long straight element as I by 2 pi r of a phi vector. Thank you.